Hi, I'm Ben-Yaakov. This presentation is entitled Intuitive Explanation of the Three-Phase Vienna Rectifier. Let me start off with the need for active power factor correction. I'm showing here a diode bridge rectifier. Here's the line, single phase. There is a capacitive filter, and this represents the load. Now, in this case, the current that we'll see at the line side will be a peaky current, and the reason is that when the line voltage is lower than the capacitor voltage, there is no current flowing, and only when the voltage of the line is higher than the capacitor, say here, then there'll be a current, and this is why this will be a peaky current, and the harmonic content of this current is something like this, the many higher harmonics with sizable value here, amplitude, okay? These are the higher harmonics, 3, 5, 7, etc. Now, there are now standards which are enforced in just about every country now, which require that the value magnitude of these harmonics will be fairly low, so that the current will be just about like a sinusoidal waveform coming here from the line. And here is the limit for the IEC 61000 norm here. So what it says is that, say, for the 13 harmonics, the value, the magnitude of the current of the amplitude of this harmonic will not exceed this value. This is in amp. While if you are using a regular rectifier, you are violating this limit, and you do need some sophisticated rectification scheme like active power factor correction, which we are going to talk about, in order to be below the limit here. The classical power factor correction for a single phase is shown here. It is based on a boost. We have here a diode bridge, so that we have a pulsating voltage here, rectified voltage. And the way this thing works is that on the one hand, it keeps the voltage at the output to a certain level. Of course, there's some ripple to it, but the average is controlled by this feedback. And also the current that is seen here at the inductor, and therefore the current at the input is also controlled such that the current of the line will be sort of close to sinusoidal waveform. So let's see how this thing works. Well, as I've said, it's based on a boost converter. This is a boost converter, an inductor, switcher, diode. This is a filter, and then we have a load. And if we look at this point, this is the waveform we're going to see. Because when the switch is on, this is a short. When it's off, we see the full output voltage. So we see a pulsating voltage like this. And the average here is, of course, the height here times the T off. This is this time here. And then divided by Ts. So this is the average voltage here of this pulsating voltage. Now, we know that in steady state, the average voltage on an inductor is going to be 0. So the average current is not drifting to infinity. So the average here is 0. Therefore, the average here and average here are to be the same, which brings us to this relationship that the average voltage here is equal to V out times D off, which is this voltage here, and this should be equal to V in. Here it is. And then from this relationship, I'm getting the classical voltage transfer ratio of a boost converter. V out over V in is 1 over D off. So this is the basic operation of a boost converter. In the case that the input is sort of pulsating, a rectified sinusoidal waveform, as we have in the power factor correction, and assuming the capacitor is very large, so the voltage here, the average voltage is about the same, the ripple is small, then obviously we have to change the duty cycle so as to accommodate the fact that V in is changing all the time. Say V out is constant, but still V in is changing. We know V out over V in is 1 over D off. So D off needs to change during the period, or half the period I should say, like a sinusoidal waveform, So D off is not constant and is changing all the time. And this is to make sure that this ratio is maintained. But what about the current? This doesn't say anything about the current. The current could be any value here as long as this ratio is maintained. So in order to control the current, you need an extra loop that will in fact change the duty cycle so as to accommodate the current or force it. So let's see how it works. We have a feedback from the output. We are sensing the pulsating voltage after rectification. And by this multiplier, we're changing the height of this. This is in fact now a reference signal. And now we are comparing the current flowing here. After passing through a resistor, it becomes a voltage. So we compare the voltage here to the reference voltage. And any deviation will cause a change in the duty cycle. So the duty cycle is forced such that the current will follow this reference signal. Once we have the current of this form in this inductor, then beyond the diode, it's going to be a sinusoidal waveform. So the point to understand is that the control of the power factor correction is not directly by the modulation. It is done by sensing the current and how it deviates from the shape that we want it to be, and then driving the modulator to produce a duty cycle that will be correct for the instantaneous voltage ratio that we have here and the current that we want. For the current, we would need some sort of a trimming or a step change in order to bring it up and actually to overcome drops of resistors, parasitic resistors that you might have in the circuit. So this is very important to understand that we are having here a current feedback that forces a current through this inductor and therefore forces the current of the line. And now I'm turning to the Vienna rectifier. This is the classical Vienna rectifier configuration. In fact, this is the first page of the patent, and it is a European patent, and it was filed by now Professor Johann Kohler. In fact, it was filed by, as far as I know, while he was still a doctorate student. It's 1993, and he is the sole inventor. So this is the Vienna rectifier. It looks like scary a little bit. There are many switches, and let's have a look at it. Many switches, and then we have diodes, etc. And then there's a split capacitor. So it looks kind of complex, and there are some other configurations to it. Here is another configuration. It's the most modern one that is used today, the Vienna rectifier. And here from Wikipedia, I'm showing all the various configurations that you'll get depending on the state of these switches. These are switches that are on and off, and you get all this. All this looks very complicated. So let's try to simplify it. And in fact, it is very simple, as I'll show in the following. So I'm starting with a bridgeless bipolar active power factor correction circuit. It is very similar to what we've seen before, except for two facts. Number one, we don't have a rectifier here, diode rectifier. Secondly, we have a bipolar switch, meaning that there is no diode here like a regular FET, and this can be realized by either a back-to-back MOSFET, such that when these are off, there is no current path because of the back-to-back diode, or it could be realized, this bidirectional switch, by this arrangement of a bridge diode plus single MOSFET or other switch. And in this case, what is going to happen is that when the current is, say, this direction and the transistor is on, the current will pass this way, and then when the current is in the other direction, it will also pass through the MOSFET. So therefore, when the MOSFET is on, there is a short here or conduction path here, and when it's off, there's no conduction. So it's a bidirectional switch. Now we have two diodes, one here and one for the negative half cycle, because it works two ways. When the voltage here is positive, it works like a regular boost converter, the positive boost converter. But when the voltage here is negative, this diode is now operating. The switch is still the same switch, it's a bipolar, so it can work with either positive or negative voltages. So when the switch is on, it is sort of shorting the input, current is building up, and then when it is off, it is passing through the diode and this capacitor. So we're going to have a voltage on this capacitor and this capacitor, and if everything is balanced, these will be the same, and the output is now coming from across the two capacitors. So this is a bridgeless bipolar active power factor correction. Now I'm going to build a three-phase power factor correction circuit. I'm starting with the single phase, and then I'm adding another phase. Okay, this now is another source, another line, you might say, shifted by 120 degrees. We have the same arrangement here, this diode, and then we have this diode. Okay, these are not interacting, they are not interfering each other because they are working against this capacitor. The voltage is supposed to be constant except for some ripple. So now I can add another phase, again shifted by 120 degrees, and we have the corresponding switch and diode. So now we have here, in fact, three independent active power factor correction. Each one can be controlled, the current can be controlled by turning on and off the switching, as we have seen before. The reference will be the corresponding voltages of each one of these phases, and we are sort of summing up the outputs here across these capacitors. Now, this being a three-phase system, we know that the sum of the currents of the three phases shifted by 120 degrees is zero. So when you sum these currents, you get zero. Therefore, there is no average current flowing here. Okay, there's no need for that, for the average current, because the sum of these is zero. And therefore, I can actually disconnect this line. Okay, so what I see here now is three phase. This is the neutral. We have control on the switches such that the current will be sinusoidal waveform, and here we have actually accomplished the need for power factor correction of a three-phase system. And this is exactly what we have here in the Vienna rectifier, although it's drawn differently, but basically it's the same thing. We have the three phases here, we have the switches here, we have the diode. So let's have a look at it more closely to one of the phases. So here is the phases, this is the switch, here's the switch going to the middle, this is the switch going here to the middle. And then we have here two diodes. Well, there are two diodes here in series, so basically it's a function of a diode here and a function of a diode here. So basically you see that the Vienna rectifier is just a realization of the three power factor correction for the three phases, as I've shown before, step by step. Now, this configuration is also the same, because what we have here is the diodes going to the two capacitors. Here's this diode and this diode. So let's talk about this phase here. This diode and this diode. This is the inductor here. And then we have the switch. This is a bidirectional switch between here and the middle. So we have a bidirectional switch between here and the middle. So this is exactly the same configuration. Now, what about modulation? Well, as I've said, these are actually independent three active power factor correction systems, single phase power factor correction systems. So you can control each one independently. So this is actually a scheme for one of them. So there are three units like that for a three-phase. I'm talking about the major issues here. Let's forget about the harmonics, which I like to leave it this time because this is a preliminary or introductory video. So we measure the voltage, which is the reference. We measure the current. We compare the voltage to the current, but the voltage is sort of modulated by the height, or the shape is changed so as to control the output voltage, as we have in the single power factor correction. And then we have a compensator to stabilize the system, and a modulator. This is a classical modulator in which we have a triangular waveform, and we are comparing the error signal to the triangular waveform to form a PWM signal, which is fed to the switches here. And then, in order to make sure that the midpoint is kept constant, and also we measure the total voltage, we have an extra loop. This is for the total voltage, but then we have also for the midpoint, so that if there is some imbalance between the current and there is be a tendency for this point to shift, this feedback will correct it back to the midpoint. So this is an extra precaution, very important, so to make sure that the system is balanced automatically. So this is a regular modulator approach. There's another approach which is based on hysteretic control, and here I'm showing a PSIM simulation implementation. We have the Vienna rectifier, and here's the control. Again, we measure the current. We compare, these are the currents here. We compare them to the voltage, but after some modulation as to keep the output voltage constant. And then it goes into a window comparator, such that when the voltage or the output here is higher or lower than the window, it'll kick one way or the other, and this will in turn turn on or off the switches. These are the bidirectional switches. So it's the same thing, except it's a hysteretic control. It's simpler, and by the way, hysteretic control is stable, so the compensation is simpler. Already there's no compensation here, no phase compensation. And here is a result of the simulation, PSIM simulation. This is, say, phase 1A, and this is the signal modulating the MOSFET, okay, the switch. Interesting, we see here some voids, okay? There are some periods in which there's no signal here, and nonetheless, the current seems to be okay. There's no breaking or no changes in the current. Well, why is this? Well, there are two reasons for that. For small changes, you'd expect it in a hysteretic control because of the numerical calculation. Well, it's not noise, but it's like the numerical finite resolution, and therefore you might expect some variation and jittering, which is okay. But there is another reason which is very important, and that is the following. In a three-phase system, here I'm showing the voltages, the sum of the current is 0. So suppose this represents the current. So we know that the sum of the current is 0. So if you control the two of them, the third one is automatically coming out to be correct. So therefore, you can actually control the two lines, and the third one will sort of follow the one. And this is why, even though there's a gap here, the current is okay for this phase. Now, for the control, we do need to have a sensing of the voltage referred to the neutral. Now, if the neutral is not available, you can sort of generate an artificial neutral point by having three capacitors which are sort of summing up, and this will be like a neutral point. So then you can measure the voltage across this capacitor, which also helps sort of to, you may have also a high frequency filter here. So this will be a cleaner waveform than just looking at the line itself. But here you have the reference neutral, artificial neutral point, that you generate with the three capacitors. Now, it should be pointed out there are many types of modulation which have many advantages, which I'm not going into. This is an introductory video. There are many papers which discuss it, and of course, they are available on the web. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.